All right, so today we're going to cover the last material we're going to see this semester. We're going to cover this idea of oscillations. And as we get into this idea of oscillations, we're going to start with observation, and we're going to build out the mathematics to support those observations and see if they're true. And then next class session, we'll do some problem solving involving oscillatory motion. So first things first, we need some definitions. How are we going to define oscillations? When we take a look at an oscillating object, such as a pendulum, up here I've set up a mass and string to give us a nice little pendulum motion. We want ways to describe certain aspects of this pendulum. What aspects of this pendulum might we care about? What do we think? What quantities might we want to describe? Momentum? Momentum would be difficult. But certainly we want to know something perhaps about the velocity of this object, and we will seek out a way to describe the velocity. But that's a complicated story. We're going to get to that much later. What other characteristics might we want to describe? The mass. We might care to know how much mass is on this pendulum. We might want to know that because perhaps if we change the mass to something heavier, we get different behaviors. We'll see if that's true a little bit later. But yeah, mass is absolutely one. What else might we want to know about this pendulum?
What's frequency?
Frequency. What does frequency mean? Has something to do with how quickly it's going back and forth. There are actually two ways we measure the time for motion to happen when it oscillates. We might consider time in two ways. We might consider time as being the period of motion or the frequency. Both of these tell you how quickly it moves back and forth, but in different ways. The time period, and we'll describe this a little bit more, the time period is a straight measurement of how much time passes before restarting the motion. So you take out stopwatch, start the stopwatch at one end, end it when it gets back. That is your period. It's the actual time it takes to pass it. However, a lot of times with oscillatory measurements, the time becomes quite small, in which case we describe frequency. What is frequency? Frequency is the number of times the motion repeats itself in a second, or in a minute, or in an hour. We'll discuss more about this time aspect of oscillatory motion soon enough. What else might we want to describe? Any other ideas? The height. Perhaps we want a way to describe the height, right? Because we can set our oscillation to happen over a small distance. We could set it to happen over a larger distance. We might want to know something about the height, or in this case, with oscillatory motion, we call it the amplitude. What else might we want to describe?
The length of the string.
Perhaps we want to know how long the string is, right? Because if we take this string and we pull it way up here, we might have a shorter pendulum. Perhaps we get different motion. So with our pendulum, we have all of these different definitions. Length of the string. Along with velocity, we might care to know something about the position at any given time. We also might want to know the acceleration. Ideas we will explore, but we're going to start off with how the actual build of the pendulum affects different quantities. Before we get into the pendulum, let's discuss this period and frequency bit. And I like doing this by starting out with a measurement of heart rate, something I think we're all familiar with, because heart rate is a good description of one of these two quantities. Now we're all going to take our own heart rate right now, so everybody take your 2 fingers, find your pulse. You can find it on your neck, you can find it on your wrist. Let's try and find it. I'm going to take a moment. If you're having trouble finding it, double check with your doctor that you have a heart. All right, so we all have our pulse. Yes, we can all feel it. It's easiest to feel it on the neck, I think. Okay. You're going to count how many times it beats. In a 10-second time period, I'm going to tell you to start counting, and then I'm going to tell you to stop counting. Sound good? All right, everybody, let's go ahead and let's start counting in 3, 2, 1, start. Stop. Okay, write down how many beats you count. That was a 10-second period. That was a 10-second period. So right now you have the number of beats in a 10-second time period. The number of beats in a 10-second time period. Now this description of how many times something occurs over a given period of time is a definition of frequency, although our frequency usually has different denotions of time. So instead, let's convert this to beats per minute, the more familiar term for heart rate. How are you going to do that? You're going to multiply the number you just calculated by 6. If it beats that many times in 10 seconds, it'll beat 6 times as many times in 60 seconds. So take that number you just found, multiply it by 6, find what your heart rate is in beats per minute. Now, when we think about frequency, we really want to consider this idea that it's counting up how many occurrences something happens over time. How many occurrences of something happening over time. In this case, how many times does your heart beat in a minute, for example? Does somebody want to share what their heart rate is? Takers.
I got 72.
72. 72 beats per minute. What does that mean? That means there's 72 occurrences of a beat happening per minute. The frequency of the beats is 72 happening in a minute. Does that make sense? This is a description of frequency. But perhaps we don't want to know frequency, perhaps we want to know the time period. The time between beats occurring. Want to know how many seconds occur between individual beats. How are we going to do that? Well, that's asking a question of the period. To represent period, we use the capital letter T. Capital letter T because it's a time that occurs and it's a special time, so we give it a capital T. T is representing your period. And how do you calculate a period? Well, the period, we could grab a stopwatch, wait for a heartbeat to happen, start the timer when one heartbeat starts, end it when the next heartbeat happens. But that's going to be an incredibly short period of time, hard to measure. So instead, what we're going to do is use the frequency measurement we just took. And the period happens to be the inverse of the frequency. So for example, the period, if your heart rate is 72 beats per minute, the period would be 1 divided by 72 beats per minute. You calculate this up and you end up with, for everybody in here, we have different heart rates. Certainly if it was 72 beats per minute, you would end up with 0.0139 minutes per beat. In other words, 0.0139 minutes occurs between each beat. This is not a useful measurement of time, though, a hundredth of a minute. So instead, let's convert this to seconds, something more of the scale of our heartbeat, right? So in order to convert this to seconds, we say there are 60 seconds in 1 minute. So we take this 0.139, multiply it by 60, and you can find a period of 0.83 seconds between beats. A little bit less than a second. So a second occurs between each beat. Again, this is a measurement of period. Period being the time that it takes for a pattern to repeat, the time that it takes for your heart to beat. Does this sound okay? So we have this idea. Period and frequency both describe the same physical quantity or the same physical phenomena in relating to how quickly this object is repeating its motion. A heart rate, good example of it, something we're more or less familiar with. Now, typically speaking in physics, minute is not our base SI unit. Second is our base SI unit. So if we want the frequency not in minutes but in seconds, we do a unit conversion. And in this case, 72 beats per minute. Would give you a frequency of 1.2 beats per second. More standard SI unit, seconds. But there's a little bit of a caveat here. Beats is not an actual unit of measurements. It's a standing, it's a placeholder. It's to let us know what is occurring, what we're measuring. But beats is not an actual unit. That's why in the period I discarded beats. It's not an actual unit of measurement. It's a pseudo unit, meaning we can remove it so long as we remember the context in which we took this measurement. We know that the frequency 1.2 is related to the frequency of our heartbeat. And this unit of 1/2, we use it all the time. Frequency is a very powerful tool, a very powerful measurement. So instead of writing 1/2, we create this new unit to represent 1/2. We create this new unit of the hertz, represented by Hz. So we create this new unit for frequency of hertz, where 1 hertz is equivalent to saying 1 inverse second. Just the same way we define a Newton or a joule to be some combination of other units, we define the hertz to be a unit of 1/2. So that's the idea behind frequency and period. And this relationship between the two will take us a long way, because when we measure something, we're almost certainly going to measure periods, but what we usually want to know is something about frequency, and we'll go back and forth between the two. But now we return to this pendulum, right? This pendulum, comprised of some mass and a string with some length, and that's all that it takes to build a pendulum, a string and a mass. We want to know about the behavior. And specifically, we are going to ask the question, does period change with what? With mass, amplitude, or length, the other quantities. Does period change with mass? Does period change with amplitude? Does period change with length? That's what we're going to seek to try and determine from our setup here, and then we'll mathematically work it out, see if we can figure it out mathematically. All right, so taking our period, we're going to measure period because it's the easier of the two to measure than frequency. So what we're going to do is we're all going to take out our cell phones and get a stopwatch ready so that we can take some measurements of time period. But there's going to be a trick. Because if we just try to measure one period, meaning the time it takes for it to repeat motion, it's going to be a small value. So I'm going to give you an example, okay? I let it go. The period is how long it takes to repeat its motion. So we'll start it when it hits my hand, we end it when it comes back and hits my hand again. That would be the period. So we set it in motion, we would start our stopwatch, and then we would end our stopwatch. It's kind of a small measurement. A small measurement that would be relatively inaccurate. To increase our accuracy, what we are going to do is measure time for 10 oscillations. Why do we do this? We do this because it's a lot easier to get an accurate measurement for 10 oscillations than it is for a single oscillation. And then when we have the time for 10 oscillations, well, we could take that time and divide it by 10 to figure out the time for a single oscillation. So that's how we're going to get our accurate measurements of the period. Does that sound okay? So we're going to take a look at this math. We're going to start it when it reaches the left side, and then we're going to count 1, 2, 3 oscillations until we get to 10, and then on that 10th one we end. I will say start, I will say end, I will count off the 10 oscillations. This is going to be a little bit of a tedious process, but we're going to see it through. Sound good? Okay, so let's go ahead. Let's set it into motion. I'm going to say start. As soon as it gets back to my hand, we're going to count off 10, and then we're going to end it. So we start, 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. So you should have some time for it to undergo 10 full oscillations. Let's go ahead, take that number you just found and divide it by 10. That is a measurement for period. That is the period of oscillation for our mass. What I want you to do is now compare it to your neighbor. Make sure you and your neighbor got roughly the same value. Look over your neighbor's shoulder, turn around to see your nearest neighbor. All right. Does anybody want to share what their value of period is? Raise your hand.
1.87.
About 1.87. I think on average, you should get about 1.8 seconds. Some of us will have 1.7. Some of us will have 1.8. Some of us have 1.9. Some of us 1.6. It should be somewhere around that 1.8 value. So that is the period for our little mass. We are going to now change the mass. We're going to change the mass to be a larger mass. We're changing it from 100 grams to be 5 times larger at 500 grams. A very large change here. So the question is, do we think that the period will become larger or smaller or stay the same? Let's make a prediction. Everybody, turn to your neighbor, make a prediction. Do you think the larger mass will have an increased period, meaning it will take longer to swing back and forth, or a decreased period, meaning it will take less time, or stay the same? Discuss with your neighbors. Come up with a prediction. It's okay if you're wrong. So we have a guess. We have a hypothesis. I hear the word inertia. Hear the word inertia. Certainly a larger mass has a larger inertia, meaning it's going to have a tendency to resist change in motion. There's people talking about air resistance. Let's go ahead and see if we're correct. I'm going to start this in motion. And this time, instead of doing 10 oscillations, Let's do a few. Let's do fewer. Let's do 6 oscillations. Sound good? So I'm going to take the mass. I'm going to set it in motion, and we're going to do 6 oscillations of time. I'm going to say start when it comes back to my hand, and count out 6, and then we're going to end it. So we're going to start. 1. Sorry, I messed that up. Messed that up. I meant to give it a full swing before I said start. Okay, ready? Start. 1, 2, 3, 4, 5, end. Now from that measurement, determine what your period of oscillation is. Compare with your neighbor. Now we're going to keep in mind that we made a significant change to the mass. We took a mass that's 5 times as large as our original one. So any sort of change we would expect to see should be significant. But do we see a significant change here? No. You might see tenths of a second change. You will not see anything significant. Since we changed the mass in a significant way, but we did not see a significant change in period, we can say, does the mass change the frequency? And the answer is no. Or does the mass change the period? The answer is no. Sound good? All right. What else do we want to check? We want to check the amplitude. The motion I just set had an amplitude coming out to about here. We're going to test a smaller amplitude. Wait, my length just changed. Okay. 1 second. The knot just tightened and changed the length of my string. I think I corrected it. Okay, so we're going to try a smaller amplitude now. We're going to try an amplitude that's maybe about half of what it was before. So instead of coming all the way out to here, we're going to do a smaller amplitude right here. Sound good? All right, I'm going to set it in motion, but I'm going to leave it up to you guys to count off however many period or how many oscillations you want to measure. I'm just going to set it into motion. I'm going to give you guys a few minutes to determine the period. Sound good? You can do as many oscillations as you'd like. All right, I'm going to let it go in 3, 2, 1. Give you guys a second to decide when you want to start, when you want to end. This is up to you. So I'm trying to hypnotize you. Okay, put your phones down when you have a time measurement so I can visually see. All right, looks like most of us have our phones down. Now again, that was a significant change to amplitude. We're operating at about half or maybe even a third of the amplitude. The question is, do we get a change in the period? Does anybody want to offer up what their period they measured was? Angelina?
I got 1.7 seconds.
1.7, okay. Anybody else want to offer up a period? 1.5. What else?
I got 1.932.
1.932. Anybody else? Let's hear it. 1.65. All of the numbers are not deviating too far away from 1.8. Again, we made a significant change, but we are not seeing significant change. If you average together the 1.9s and the 1.6s and the 1.7s, you're going to end up with about the same period. So does the amplitude change the period? The answer is no. All right, well that leads us to the final question. Does length change the period? So what I'm going to do is I'm going to decrease the length here, and I'm going to do so dramatically. Here's my string. I'm going to wrap it around up here to give us a smaller length of string for our pendulum. Those of us interested in antique clocks will know this is how you calibrate a clock. So I decreased the length, and I did so significantly. And the question is, do we expect there to be a different period? I want you to, with your neighbor, come up with a hypothesis. I think the period will increase, decrease, or stay the same with a smaller length. All right, so we have a hypothesis. We come up with a hypothesis with our neighbor. We're going to see is it true or not. I'm going to set the mass into oscillation. Again, while it is oscillating, it is your job to determine what the period of oscillation is. So I'm going to set it to go, and you guys are going to find out what the period is. All right, I'm letting it go in 3, 2, 1. Go ahead and calculate out what your period is. All right, do we see a decrease, increase, or a constant period with our change in length? How many of us saw a increase to the period? It took longer. How many of us saw a decrease? Absolutely. And I'm not going to ask about staying the same because you shouldn't have. So what do we find? We find, does the length change the period? The answer is yes. So what does the period of a pendulum depend on? It doesn't depend on the mass that we put at the end of it. It does not depend on the amplitude. It only depends on the length as far as we know. So can we figure out why mathematically this is the case? Now we get a little bit into the theory. We're going to do some mathematics. You're going to see why calculus is important. You won't have to know the derivations, but I want you to see where the equation comes from and why we learn calculus. So we start off, as we would with any problem, we draw a picture. I'm going to draw a picture of our pendulum. Pretty simple. We have our pendulum with some mass at the end of it. And our pendulum is going to swing back and forth. It's going to swing back and forth along this arc. At any given moment in time, the pendulum will make some angle theta with respect to the vertical axis. And that value of theta changes over time, right? That value of theta as it swings downwards goes to 0 and then increases and then goes back down to 0. We get theta changing over time. We get the angle changing over time. And our pendulum has a length of string L. So we want to examine this and we want to say, okay, how do we approach this problem? We approach this problem by considering Newton's second law, that the net force is mass times acceleration. The net force is mass times acceleration, where here the force is going to be the force that is moving our object in the direction of this path. Well, what is acting on this mass? We have a tension force going upwards, as well as a gravitational force downwards. But the entire gravitational force does not cause the motion to change. It is only the portion of the gravitational force that moves in the direction of motion. I'm going to call that Fg, x. Not because x means horizontal or vertical, but x is in the direction of motion. If we play out our angles a little bit, what we would see is that the portion of force in the direction of motion is going to be force of gravity times, playing out our angle theta there, times the sine of the angle at that moment. Again, theta does change over time. Theta is not constant. Our force is not constant. Meaning our acceleration is not constant. But we still have this f gx is equal to mg sine theta. Does that sound good? All right, so we have this idea, f gx is equal to mg sine theta. We want a way to describe our acceleration. We will describe our acceleration as being distance covered over time. The distance covered is going to be, let's see, let me remember, theta is equal to arc length divided by radius. Hold on, let me remember. Length over arch. Yeah. Arc length over radius. So if we want to know about acceleration, we would write it as being length times the second derivative of theta dt. This goes back to the angular motion that we were dealing with a long time ago, where we defined alpha to be d omega dt, and omega to be d theta dt. This is converting into rotational coordinate system because our rotation is happening for our pendulum. Okay. Does this feel okay? Do we vaguely remember this rotational motion stuff? Where we go from acceleration, linear acceleration, to rotational acceleration by multiplying acceleration by the radius. You look in your little flashcards from way back then. So we have our acceleration, we have our force. We know our force is mass times acceleration, so combining these two equations will give you the net force, mg sine theta, is equal to length d squared theta dt. And I forgot my mass from MA mass. There we go. So we end up with this equation. And one thing we notice immediately is that our mass cancels out. Mass cancels out on either side, meaning mass plays no role in our equation, in how our motion changes over time. And what do you know? Mass plays no role. So already we're seeing the theory match up to what we experimentally found. Now we're left with g sine theta, acceleration due to gravity, times sine of the angle is equal to length d squared angle dt. And this looks tough. This looks tough, but we're going to make an approximation. We're going to make an approximation called the small angle approximation. What is the small angle approximation? The small angle approximation is the approximation that the sine of an angle is roughly equal to the angle itself in radians, provided theta is small enough. Provided the angle is small enough. What is small enough? Well, small enough would be somewhere around 9-10 degrees. But making this approximation, the small angle approximation that will be incredibly important next semester. Making the small angle approximation takes our equation g sine theta is equal to L d squared theta dt squared, second derivative. Takes that and it makes it g times theta is equal to length times d squared theta dt squared, the second derivative of theta. Now again, I mentioned calculus being very important here because we're taking derivatives. And here, what we have is something that when you take the derivative of it twice, you return back to what you had before. You have something that when you take the derivative of twice, you return back to the same thing you had before. And what fits that idea? Well, what fits that is a sine function. Because sine of theta, you take the derivative, you get back to sine with a negative out front. So you have sine theta, cosine theta, works as well. Both of which will take the derivative twice to get back to cosine theta with a negative out front. And we can take these two pieces and say, well, if that's what solves this equation, we can create a solution in which we take theta, actually I should have, when I'm talking about the derivatives up there, I am saying arbitrary values of theta. I should have probably used a different value, phi, because I'm using theta elsewhere. In any case, we have theta being equal to sine of some value that changes over time. I'm going to use the Greek symbol omega times t. We say this must be the solution that solves this problem. And when you do that, you end up with the equation that g times sine of omega t is equal to L times the second derivative of sine omega t, which would be omega squared sine omega t. I'm going to hand wave the negative away. There's a reason why it goes away. It has to do with direction of forces and motion. You could just trust me that the negative goes away when you start putting in directionality. At which point, sine omega t cancels out of both sides, and you end up with this relationship that says omega squared is equal to g over L. And what good does that do us? Well, it tells us one thing. It says whatever change is going on, it should only depend on the length, as well as the acceleration due to gravity. Whatever omega means, it should depend on that. And when we take a look at this, we did see it only depended on length. And could I have taken this to the moon and found a different acceleration due to gravity? Absolutely. But we are limited by being stuck on the Earth's surface. So this says, whatever change is occurring must be related to G and L. All right? Well, what does omega mean? We take a look at this sine function, and within this sine function, we can see sine is a repeating function. Omega is the value that tells us how quickly it repeats over time. How quickly it repeats over time, well, it's a description of frequency. The repetitions over time, right? Omega is what we call the angular frequency. Omega is what we call the angular frequency, which we define to be 2 pi times the frequency f. Where f is your natural frequency, the number of oscillations that happen per minute. So this tells you that 2 pi times the frequency squared is equal to G over L, or we can rewrite this as the frequency of our oscillating mass is equal to 2 pi times the square root G over L. Nope, did my math wrong. 1 over 2 pi. So it tells us the frequency of oscillation only depends, again, on the length and the acceleration due to gravity. If you didn't understand the whole derivation, that's okay. If you didn't understand the whole derivation, that's okay. I just want to show you that this does come from someplace meaningful. And in fact, this is a derivation from first principles, where I only did one hand-wavy thing regarding directionality, but you do get to some known determinative frequency. And again, what's interesting here is that your frequency only depends on the length of the string. Meaning that you change the length, you change the frequency, and that's the only way you can really change the frequency of your oscillating object. If you want the period, you take the inverse of that, right? It'd be 2 pi times the square root of length over g. But this gives you your oscillating pendulum. Of course, pendulums are not the only oscillating objects. There are many oscillating objects in nature, and that's why we seek to discuss this mathematics of oscillations. One other place where we see oscillating objects is with a spring and mass setup. So I put a spring on a mass, and I set the mass to oscillate. It goes up and down. We can do the same thing we did. We can measure the period. We can say every time it gets to the top is one oscillation. So we start time it, we see it undergo some change. We make a change to it. We say, I want to perhaps add more mass. So we add some more mass to this. Did this in the wrong order. Nope, that's what we're looking at there. So you add some more mass. If you add more mass, you can see, well, the period does change, and in fact, it seems like the period increased with the increase in mass. So more objects than just pendulums oscillate. We have springs that oscillate as well. And with this spring oscillation, we can start to have discussion of other objects in nature that behave like springs. Other objects in nature that behave like springs, well, any sort of a chemical bond behaves like a spring, and the vibrating motion in a chemical bond is described by the same exact mathematics of an oscillating spring. So it's a powerful tool to be able to understand how does this motion behave. And again, we do a similar sort of mathematical frame where we have where we take our spring and our mass, and to simplify things, I'm going to put our spring on a horizontal. We have a spring and a mass, and if we push the mass in, it's going to vibrate back and forth and back and forth. What we would see, F equals ma, the force on our spring is going to be Hooke's law, F is equal to negative kx. and that's equal to the mass times the second derivative of x, dx dt squared. Now hold on, this looks familiar. This looks pretty similar to what we had over here, except for now we actually see the negative sign with directionality. That's good. When we take a look at this again, the only thing that can describe this motion where we take the derivative of something twice and get itself back with a negative, the only thing that solves that is a sine or a cosine. So I say x is equal to cosine omega t. Just like I did over here with theta. I said theta sine omega t, I could have used cosine. You follow through with the same exact mathematics, you plug in cosine, you take the derivative of it twice, plug in cosine to kx. Minus k times cosine omega t. For the left-hand side of the equation, on the right-hand side, we have mass times the second derivative, omega squared, cosine omega t, negative outside for the derivative of cosine twice. You get the cosines canceling out, and you can arrive at a very similar formula to the pendulum. You arrive at a very similar formula where you can find that the frequency of oscillation for a spring and mass setup is going to be 1 over 2 pi times the square root of k over m. This is the frequency for spring and mass, behaving, again, very similar to the frequency for a pendulum. Just the difference is spring constant k instead of acceleration due to gravity g. Well, that's interesting. Both of those are the driving forces of our oscillating object, right? The spring constant is what determines how strong the spring pulls. G determines how strong gravity pulls. And you have the length as well as the mass being different in either equation. But both of these follow a very similar pattern. Just to be explicit, this is only for spring and mass, and this is only for pendulums. But this behavior is more widely applicable than just with spring and mass and just with a pendulum. Do we feel okay about that? So we have a way to theoretically determine. We have a way to theoretically determine behaviors of our different oscillating objects. But what if we want to know how behavior changes over time? What if we want to know position, velocity, and acceleration? Right? If we want to know position, velocity, and acceleration in general, we say that our position is going to equal, I'm going to put a space here for a second, is going to equal a sine or a cosine, does not matter which you pick, times 2 pi frequency times time, where t changes over time. This tells you the position of your oscillating object. You switch to theta if you want to do a pendulum, x if you want to do a mass in a spring. Either way, you get this behavior. Now, I left a space there. Why did I leave a space there? I left a space there because there is some maximum value that our mass oscillates to. Some maximum value that our mass oscillates to, whether we're on a pendulum and how far away do we go or how far up and down do we go on our spring and mass. And this maximum value is the amplitude of our oscillation. So we say that our position is given by the amplitude multiplied by this cosine function. That amplitude gives us the maximum or minimum value our oscillating object goes between. And this tells you exactly where your object will be at any point t in the future. You ask about something perhaps like the speed of the oscillating object. Well, how fast is it? How fast is your oscillating object going? Well, speed is easy. Derivative of position. Take the derivative of your position. What's the derivative of cosine? Negative sine. So what is your velocity? Negative a cosine 2 pi frequency times time. And then you take this and you multiply it by everything on the inside, multiplied by 2 pi f. I didn't really have enough room on the board to write that. You multiply it by 2 pi f. And that will give you your velocity at any time in the future. We'll return to that in a second. Acceleration, should you care to know it, would be the next derivative, which would be amplitude times 2 pi f squared negative cosine, oh, I was supposed to switch to sine, cosine 2 pi f times time. So we have here the position, the velocity, the acceleration, found by just taking derivatives. And I'll clean up this second line because that is going to bother me. So we have our position, our velocity, and our acceleration. Now, why is the velocity important? The velocity is important because it can tell us something about the energy involved in our system. Well, how do we find the energy? The energy is made up in part by kinetic energy. Kinetic energy being 1/2 mass times velocity squared. Now, this isn't super important right now. But knowing the energy of an oscillator is very important when it comes to electricity and, more important, electromagnetism when we start looking at things like light wave and energy transported over waves, which waves are oscillating objects. But there's a reason why we would want to know the velocity, because it tells us something about energy. Okay, there's a lot that we covered just now. A lot of mathematics. Dealing with differential equations, not the easiest thing in the world. And going back to something I said many weeks ago, why don't we use Hooke's law with Newton's law? The reason why we don't typically use those together is because when you use them together, it does lend itself into being this differential equation that we just solved. So you can use Hooke's law with Newton's law. It's just a little more complicated than just what we've seen previously with Newton's law. Okay, I want to do an experiment here. I want to do an experiment to see how accurate these measurements are. And we're going to specifically look at a pendulum. What I want to know is, dealing with the practice problem, what length pendulum matches the period of your heart rate that we took at the beginning of the class. Everyone here had a different heart rate, everyone will have a different length of the pendulum. I want you guys to calculate what length pendulum matches the period of your heart rate. Go ahead and calculate that out. Pretty simple enough calculation. All right, so how do we find the period or the length that matches our frequency? We start off, or the length that matches the period, I should say. We start off with the period, with the equation we found earlier, that frequency for our pendulum frequency is 1 over 2 pi times the square root of g over L, where g is our typical 9.8. So we start off with this equation we found earlier. Did I write it up on the board right? Did I get it g over L, not L over g? Sometimes mix those up. We want to match it to the period, so let's go ahead and write up. Just throw that marker away. Period, which is the inverse of the frequency. We want to match it to the period we found earlier, so easy enough. Solve for period. I know what the period is, right? Our period is dependent on the heart rate that we found earlier. So solving this for the length, we find length is equal to period divided by 2 pi. End up having to square it and multiply by g. I think I did my algebra there correctly. Plug in your values, and you should end up with something around 20-ish centimeters. Is that right? Did I do my math right? Let's get a sampling. Who wants to share the length that matches the period of their heart rates? Does anybody want to share the length that they found? Give you guys a little longer.
Squared.
All right, who wants to share their length?
29.26.
29.26 centimeters. All right, so we make sure we think about units here, right? G is in meters per second squared. T should be in seconds. Did we convert to seconds? So for most of us, the period between heart beats should be around 1 second. If you're 60 beats per minute, right? You should have 1 second period. Yes? All right, if we take 1 second to be the period, we would have 1 second divided by 2 pi. Square that, and then you multiply it by 9.8. Doing this math, you would have 1 over 2 pi is 0.159. Quantity squared multiplied by 9.8. 0.159 squared. 0.025. 0.025 times 9.8, I'm excluding units just for expediency. 0.025 times 9.8 should be about 24 centimeters, 0.24 meters. Should not have seen anything on the order of a few meters in length. It should be somewhere around that 20-ish centimeter or 20-ish centimeter range. All right. Now, in theory, a pendulum of length 24 centimeters should have a 1 second period. In theory. If our theoretical derivation of an equation works out, a 24 centimeter pendulum should have a period of 1 second. Now, why do I ask to match it up to your heart rate? Well, this is part of an experiment I have ongoing throughout the years. There are people that believe that if you match a pendulum to your heart rate, you can hypnotize someone. We'll see if anyone in this class gets hypnotized by this experiment. But for the most part, we're seeing, does the physical theory match up? Will this have a 1 second period? Everyone take out a stopwatch. We'll see, does theory match with experiment? I'm going to set it in motion. Okay, I'm setting it in motion in 3, 2, 1. Find the period. So then the question becomes, did we get about a 1 second period? Yes? Wonderful. That means that all of the math that we just did to get this very abstract, equation ends up working out. The theory matches up with the experiment, and that's always a good sign. We're going to end there. Next time we're here, we're going to just work on some practice problems involving pendulums, involving springs and masses. I have a new card for you guys to grab before you head out. I want to give you a reminder that next week on Monday from 11:30 to 2 o'clock is your final exam. It will be 4 questions long this time. Your 4 questions will involve a question on oscillation, the stuff that we're dealing with today, as well as questions related to fluid statics, fluid dynamics, and there will be a collision problem on your exam as well. On Wednesday, after class, I will have a practice exam during office hours. I strongly encourage you to attend if you can. And I will be sticking around after class today, answer any questions that you guys might have. Are there any questions, thoughts, comments before we wrap up today? All right, make sure you get one of these new green cards before you head out. And we will end class about 5 minutes early today. Again, I will be sticking around till probably around 2 o'clock, answering questions.
So I did the exam.
Okay, 1 second.